Okay, so here we're going to do one more. Here you can see the question where it was. Okay, let me. Yes, this was the question of probability. So we have to do a plus 2b plus 3c plus 2d plus e for each one. So that was I was doing 1 plus 2 into 0, so this will be again 2 plus 2 square, it will be 4. So heuristic value for this string is just 4. And then after this, so this is our 4 candidate. Each candidate have 5 bit string. Then we need to calculate the probability. Probability will be like 4 by 65. This will be the probability. Then 36 by 65, all of this. Then ex will be 4 into multiplied by probability. So we will multiply it by with this 4. Then with actual value will be just the whole number. So this is approximately it will be equal to 0. Then this will be equal to 2, then 1, then 1. And again, this is again we are trying to find a adjacency list, adjacency part, or adjacency representation. Then and we are going to, here we are trying to find ordinal representation. Let me check 11. Yeah, original representation. But remember, the original representation, how to find it is like we're going to first check. We're going to first check for. We're going to first write it down like this. The for which part we are going to find original representation. Like we're going to find the original representation for this tool, right? DIJONH like this. So then we will write ABCD up to O. Then for A is 1, then B is 2. Then we'll write, so what was the value, first value? It is D. So we will write 4 first. Then we will cut it. So E will be again updated to 4. F will be 5, G will be 6, H will be 7, I will be 8. So I will be 8. The next value was I. We will cut it and 8 will be updated. And then after I, whatever the value was there, it will get updated. So J will be updated as 9. Yes, 9. And K as 10, like that. Then J will update it as 8 after I's cut off. So then I will cut O will cut. There was nothing after O, so no, nothing will get updated before it. It was 12, and then N will cut. So N, there was also nothing after N, so nothing get updated. Then H will get cut. So H was 7. So this will all of these things will get updated. So like this, after all of the it will become this representation. This will be called as ordinal representation. So here also it is saying like what was the question? Question was like there is given a path representation. We need to do partially mapping crossover from 6 to A. We will write it as from P1. For C1 side, we are going to put as this BINGO from 6 to 10. and remaining city will copy from P2 to C1. But we will map this like we will map. So how to put this one like so for J it will go to B, but B will go to this, so J will be put here. Then A it will go to I, then I will be put here. So A will be put here. For N was so L will be put here. So like this, and our remaining city will be copied from B2 into C1 directly. For second cell, we can do that. For C2, we're going to copy from J to the E position directly, and then we will map the 6 to 10 position from P1 to P2, and we will put in C2, and the remaining C2 we can just directly copy from P1 to C2. The next question. Next question is like we are giving, so this is same as partially mapping question. Then again, what was the question? The 5 number. It's an order crossover. So what we will do in order crossover from 6 to 10, uh, so we are going to find out the solution as MJA LK BINGO. This one we are going to find out the solution. But what they're saying is how you are going to find out. So for order crossover, we are going to from 6 to 10 we are going to write. So okay, so for order crossover, we will write this value, which what value was not in the uh, those will be directly written MJALK, and then but this value BINGO, this needs to be selected orderly, like this need to be copied directly. Using order crossover. So if we are going to do an order crossover, it is 13. These two parents. then we need to select all the cycle. For order crossbar, we need to select all the cycle, or first cycle, third cycle, like this. So, and after that we are going to just select the, I think this is also called cycles crossover. Let me, I'll check it and I'll uh, then for each cycle, first cycle, second cycle, then we will number it as they were found, uh, and it will be odd or even. If C1, the first cell will get odd number of cycles from P1 and even number of cycles from P2, and C2 will get even number of cycles from P1 and odd number of cycles from P2. That's it. And merging also easy. I mean, if you know that we have 6 subtour, this is subtour, and we are going to select it in descending order, 1, 16, then 18, 96, and we need to see if it is merged or not. So we're just going to say that, okay, let me check. The first city, which was 116, it was uh, D, right? So D is in present. D is present in BDB. D is present in BEB. So we'll just connect it. Then we'll, yes, merging is possible. Then we will connect A like this, because A is present in BAB, is in like this. So we'll connect it. Then CD, then we, but DF we cannot connect further because DNF is already got merged. So no further merging. So no further merging will occur. Today we are going to discuss differential equation, specifically partial differential equation. But before that, we need to know some formulation in order to derive a solution of some differential equation, whose are particularly ordinary differential equation. So for this, we will first look at, we'll first look at the equation of type n is a function of t, and where we will see where while we're differentiating n with respect to t, let's say this is equal to some constant lambda minus lambda of nt. So if we integrate this, if we take the integration side, dn by n, because we will use the separation of variable, and we'll integrate both sides, and integration of dn by n is equal to minus integration of lambda dt. Then we will get ln of n is equal to minus lambda t plus c, or we will get ultimately the solution as n is equal to n naught e to the power minus lambda t. So this is a solution of ordinary differential equation, which will be very useful in order to solve partial differential equation. When we will solve the partial differential equation or convert partial differential equation into ordinary differential equation, then we can use this formula. So now this is again homogeneous equation, this is again ordinary differential equation. So the first order ODE or ordinary differential equation, m of the function m is of x and y, and with dx plus nxy of dy is 0, is homogeneous. And how we will know that it is homogeneous? if m of xy and n of xy are homogeneous function of the same degree, or if it can be put in the form y dash is equal to f of y by x, then we can put y is equal to vx. So we can basically we can substitute y is equal to vx, and then we can ultimately get into a form where y dash can be written as function of y by x. Then that equation will be called as homogeneous equation. What are the conditions for exact equation? If m of xy dx plus n of xy dy is 0, it will be exact if this m xy dx plus n xy dy is exact differential of the df of xy. And the necessary condition and sufficient condition for this equation to be exact is partial of m with respect to y is equal to partial of n with respect to x. Now we need to find out non-homogeneous equation. So for non-homogeneous equation, dy by dx plus p of x into y is equal to qx. Now the coefficient of dy by dx is 1. We can see that. Then it can be reduced to exact by multiplying one integrating factor, which is nothing but e to the power integration of px dx. And if we multiply this, then we will get the solution of y as integration factor, which is nothing but e to the power minus integration of px p of x dx, then integration e to the power e to the power integration of px dx into qx dx plus constant. This is the solution y. And if it is in the form of dx by dy plus p of y into x is equal to q of y, then we will multiply this with integration factor e to the power integration of p of y or q of y into dy, and we will multiply this and we will get the solution as x is equal to e to the power integration of minus integration of q of y dy into integration of e to the power integration of q of y dy into r of y dy plus c. So for example, for homogeneous equation, so this function f of x y x square plus xy plus x square, this is homogeneous in order 2, because the highest order is 2. So if I substitute as x as kx and y as ky, then if we do this squared k square x square kx ky, we can write it in the form k square f of xy. So we can see the order is 2, or 2x minus y y y prime or y dash is equal to x minus 3y. This is a homogeneous. How we will know this is homogeneous? Because we can write this y dash is equal to x minus 3y divided by 2x minus y. This is another example. This is different example. This is different example. And then this can be written as 1 minus 3y by x, taking dividing by x in this both side, upper numerator and denominator, divided by 2 minus y by x. So we can write this equation in the form of y by x. So this is a homogeneous equation. Now next is we will take an example how to find out if the given equation is exact form or not. To do that, we will equate them to 0. Then we know x dy plus ax plus y dx is equal to 0. How we get that? Well, y dash means dy by dx, so it will be x dy plus ax plus y will be multiplied with dx is equal to 0. After that, ax plus y dx, this term will be called as m, this term will be called as n, and then if we take the partial of m with respect to y, which will be equal to 1, and partial of n with respect to x will be equal to 1. This should be n. This should be n. So this should be n or x, because n is nothing but x only. Yeah. So we get this idea, and so this both of these differential are equal. So this equation is exact. So from this line we can see that this equation will be exact. Now the function is can be written as mx dx and plus this function can be written as integration of mx dx plus zy. So integration of equation 1, this is the equation, integration of equation 1, because we know m of x is equal to x plus 1. Integration of equation 1 with respect to x, keeping y constant. So we will get a constant in terms of y. So if we do that, then we will get ax squared by 2 plus yx plus a constant, which will be the constant of z of y. Then we will integrate, we will differentiate this third equation. This is the third equation. We will differentiate this equation. So we will differentiate it. And with respect to y, keeping x constant with respect to y. X will be here a constant. Now if we do that, then what we will get, see the function with respect to y, then this will become 2 will be cancelled, and it will only left is on differentiate with respect to y. So this will become 0, because with respect to y this is just a constant. Then we differentiation of yx will be x with respect to y, and differentiation of z of y will be dz del z by del y. Now we already know this is equal to x. This is equal to x. So what we get is the partial of z with respect to partial of y is equal to 0. So the z is nothing but a constant c. So the final function will be ax squared by 2 plus yx plus. So why we and for this calculation, for finding out this f of x and y, we have used the the first formula, the first equation to integrate and then differentiating the result with respect to y. But we can do similar thing with the second equation also. First integrate this equation, then differentiate with respect to x. That will also give the same answer. Now non-homogeneous equation of this type. So this is also the same. We just there is a non-homogeneous equation that uh, dy by dx plus p of x into y is qx. Qx is not equal to 0. That's why this is non-homogeneous. Now how to make it an exact equation so that you can find the solution? Well, we'll try to find out an integrating factor. So integrating factor will be e to the power this p of x. P of x is nothing but ax. So integration of e to the power integration of ax dx. A is a constant, so x squared by 2, ax squared by 2. Now you will find out the solution as e to the power and multiplying with integration factor e to the power minus ax squared by 2 multiply with integration of qx. Qx here it is bx. So b will be on the outside because it's just a constant. Then x integration vector e to the power ax squared by 2 dx plus c1. And if we put ax squared is by 2 is equal to t, so dt by dx will be just ax because 2 will be cancelled after differentiation of x squared 2x. So 2 will be cancelled. dt by a is nothing but x dx. So we can substitute x dx as dt by a, and I can we can put 8x squared by 2 as t. So e to the power t, this will become dt, and outside b by a. So the answer will be integration of e to the power t is e to the power t plus c1, and outside also the function will be e to the power minus t. So e to the power minus t, e to the power plus t will become 1, and b by a plus c1 e to the power minus t. So minus ax squared by 2. This will be the solution. So next we are going to discuss the second order differential equation. So before that we need to know about linear dependence and what is linear independence. Now two functions are linearly independent if there is no uh, linearly connection between them, or in other words, if c1 and c2 are any two constant, and if c1 f1 plus c2 f2 is equal to 0, that will be only true when c1 and c2 both are is equal to 0. Or in other words, if there are lots of coefficients c1 c2 up to cn, and if we write down an equation where c1 f1 plus c1 f2 up to cn fn is equal to 0, this will true only when all of these constants are equal to 0 simultaneously or individually. And the two solution of this two solution y1 and y2 of second order ODE, because in first order ODE we will get one solution, in second order ODE we will get two solutions. So the solution y1 and y2 of second order ODE are linearly independent if the Wronskian of y1 and y2 is not 0. If Wronskian is 0, then they are dependent. Wronskian is the determinant of y1, y2, y1 dash and y2 dash. General solution of second order ODE, uh, uh, let's take in general equation d square y by dx square plus p1x, which is a function of p1 is a function on x dy by dx plus e2x into y is equal to g of x. This is not homogeneous, so this is most general solution. So how we will going to find out? Well, if the roots of this equation are real and distinct, then solution will be y is equal to c1 e to the power m1x plus c2 e to the power m2x. If root are equal, then the solution will be c1 plus c2 e to the power mx. If roots are complex root, then we will get y is equal to c to the power c e to the power alpha x cos beta x minus phi, or e to the power phi x c1 cos beta x plus c2 sin beta x. Now we can modify this, or we can say, like, if there is a differential equation which is kind of like this, right? Okay, let me show it. So if our differential equation is like this one, then what you can do, we can take we already know this is nothing but this is nothing but double differentiation. This is double differentiation. This is the first order differentiation. This is second order differentiation. And if we take x as is equal to e to the power mx, then if we differentiate it at any number of times, it will be, in the first term it will be m e to the power mx, and in second term it will be m square e to the power mx. So if we m e to the power mx and m square e to the power mx, and if we substitute this in this equation, then we will get, if we substitute all of this value in this differential equation, then what will we get? We will get one quadratic equation, m square e to the power mx and k1 square e to the power 5x is equal to 0. There is no first order term. There is k square e to the power mx. Now we can take the common e to the power mx and m square, this will be equal to 0. So if e to the power mx is equal to 0, then these zeros are trivial 0. We are not interested in a trivial 0. What we are interested in when e to the power mx is not equal to 0. Now for that, what we will do is m square plus k1 square we will equate to 0. Then m can be written as plus minus under root minus 1 k. So k plus minus ki. I means iota. I means iota. And I square means minus 1. Now if we substitute this, and then we will get the solution as e to the power alpha x c1 cos beta x and c2 sin beta x, like this one only, because what we get a complex root. So the solution is like this. Now when alpha is equal to 0 and beta is equal to k1, because in this equation we have assumed that this complex root is root as alpha plus minus I beta. Now, but what we got here is ik1. We only got plus minus ik1. So alpha is equal to 0 and beta is k1. And if we do the substitution, then e to the power 0x is 1, so then it will be only, the solution will be c1 cos k1x plus c2 sin k1x. Now the second solution, second equation, which will be, so now we are going to study about differential equation which are in the form of z double dash, which is a function of z minus k square z is equal to 0. K is a constant, k3 is a constant. In differential form, we can write it as d square of g square z of dz square minus k3 square of z is equal to 0. Now, if we use y is equal to e to the power mx as a solution of this equation, and if we differentiate it twice and put in the place of z, then we will get a quadratic equation where the outside of this will be e to the power mx and inside will be m square minus k3 square is equal to 0. So the roots are plus minus k3. And if we use the equation y is, then it will be y is equal to c1 e to the power k3x plus c2 e to the power minus k3x. We already know that cos h as cos h k3x is equal to half of e to the power k3x plus e to the power minus k3x, and sin h k3x is equal to half of e to the power k3x minus e to the power minus k3x. Now if we use this cos h k3x and sin h k3x and sum it, then we will get half of e to the power k3x plus half of e to the power k3x, which will be equal to e to the power k3x. And if we use this in the formula, then what we will get is, and also similarly cos h k3x minus sin h k3x will be e to the power minus k3x. If we use it in our y is equal to c1 e to the power k3x plus c2 e to the power minus k3x, we will get y is equal to c1 cos h k3x plus sin h k3x plus c2 cos h k3x minus sin h k3x. And if we add, if we can common out c1 plus c2, then we will get c1 plus c2, take it as p, then it will be p cos h k3x plus q sin h k3x. Now next is finite Fourier transform. So here we have used the limit 0 to L for the Bn terms. So it is in the finite Fourier transform, if we got a function which is f of x is equal to summation of n is equal to 1 to infinity, and Bn is a series, and then Bn multiplied by sine of n pi x by L. L is a uh, unit in length, but it can be any variable. Now, how we can write or how we can find the value of Bn using f of x? So this is given by Fourier transform, where Bn can be written in terms of its infinite series, and it will be 2 by L integration of 0 to L f of x sine of n pi x by L dx. So the intuition is, if we have a function tx0 which is equal to summation n 1 to infinity, and it is written as Pn sine lambda n x, which is equal to T1. Then what can be the value of lambda n? So lambda n can be twice n minus 1 pi by twice l. So the value of the Pn will be 2 by l integration of 0 to l T1 sine lambda n x dx. So it can be written as 2t1 by l, because t1 is a constant, and it will be integration of 0 to l sine lambda n x dx. And if we put lambda n x is equal, if we put now yes, if we put lambda n x is equal to t, then dt by dx will be lambda n, because lambda n is a constant, because we are differentiating in the terms of x. So dx will be dt by lambda n, and if we use dx is equal to dt by lambda n and lambda n x as t, then it will be 2t1 by lambda n l integration of 0 to l sine t dt. And integration of sine t is minus cos t. Limit will be 0 to l, and if we use the limit and substitute the value of t, which is lambda n x, and value of lambda is twice n minus 1 pi by twice l, and take the limit 0 to l, and use the minus cos twice n minus 1 pi l by twice l, then we will get minus cos twice n minus 1 pi l by twice l plus 1. And we already know cos twice n minus 1 pi by twice l is 0 for all n. You can put n is equal to 0, then it will be if we put n is equal to 1, then it will be 2 into 1 minus 1, so half pi, so it is 90 degree. So cos 0 is 1, cos 90 is 0. So for all value of n, cos twice n minus 1 pi by twice l will be by 2 will be 0. So that is why the answer will be only this term will be equal to 0. Only what left will be this term will be equal to 0. Only this term and multiplied with 1, this thing will left. So the answer will be 2t1 by lambda nl. So you can substitute the value of lambda n, which is twice n minus pi by twice n, and you will get Pn is equal to 4t1 divided by twice n minus 1 pi. So this was actually the value which we got in our earlier equation, if it is possible. So this is not here. I will show you in later term. Now Laplace in cylindrical coordinate system. So in cylindrical coordinate system, you will get this equation using first of all we need to solve this. This is the cylindrical equation, but if we can write it in terms of phi, in terms of r, phi and z, and then we will get the solution. But here let's leave it for now. Let's try to jump into the Cauchy dimension, which occurs in atomic spectral line in classical dispersion theory and NMR theory. The function is f of x is equal to 1 by pi 1 plus x square. Then again there are transcendental function. Examples are log, trigonometry, hyperbolic. Now we are going to talk about the analytical function, and our next topic will be analytical function. So a function is analytic at x is equal to x naught if it has finite value at x is equal to x naught. Mathematically means if it is not blow up, if you put x is equal to x naught, then if the function does not blow up or blow to infinity or minus infinity, then that function is analytic. If a function is analytic, it can be expressed as infinite power of series of the form of this equation, where we can write summation n 0 to infinity a n x minus x naught to the power n is equal to a naught plus a1 x minus x naught plus a2 x minus x naught whole square up to n, a n x minus x naught whole to the power n. Now for particular case of x naught is equal to 0, then example of analytic function can be 1 if the function is 1 by 1 minus x, then we can use the power series formula. Then we can write it as summation n 0 to infinity x to the power n is equal to 1 plus x square will go up to n is equal to infinite terms. So this is an example for e to the power x, then this is sin x, this is cos x. You can see it in here. Now the main some little bit more concept which is needed in order to understand the analytic function is ordinary and singular point. This let's take an example of second order ODE. This is a second order ODE y double dash plus px y dash plus qx y is equal to 0. This has an ordinary point at x is equal to x naught. And how we know that it has ordinary point? If the function px, qx, these are analytic, if px and qx at x is equal to x naught, then this equation has an ordinary point at x is equal to x naught, this differential equation. And it will have singular point when px and qx is not analytic at x is equal to x naught. And a singular point is said to be regular, and this singular point what we will get if this function is not analytic, or this function does not give a finite value at x is equal to x naught, then it becomes a singular point. And with a singular it can be regular, where p of x and q of x diverge at x is equal to x naught, but the limit when x tends to x naught, the x minus x naught of px, and limit x minus x tends to x naught, x minus x naught whole square qx remains finite. Then it will be called as regular singularity. Now for example, let's take an example of differential equation, second order differential equation. Now this is a legendary equation, it's a special equation. It gives some polynomial, which also the solution as polynomial, which can be called as legendary polynomials. Now compare it with this equation. You can write it as p of x will be 2x minus 2x divided by 1 minus x square, and qx will be n whole n minus n plus 1 divided by 1 minus x square. These functions are not analytic at x is equal to plus minus 1. If we put 1, x is equal to 1, then this becomes 0 and it will blow up to infinity. And if we put minus 1, it's squared, so again x squared will be 1 and 1 minus 1 will be 0. Px and qx is not analytic at x equal to plus minus 1. But these are singular points. How? Well, if we take x minus 1 of px, then it will become 1, the lower n become 1 plus x, 1 minus x. 1 minus x, 1 minus x will be cancelled, and that the limit will go to, if we put x equal to 1, then limit will be 2 by 1. 2 will be cancelled, and it will be just 1. So the value is finite. So limit, however, the limit x at x is equal to plus minus 1 is infinity, or limit does not exist, but at x minus 1 p of x is finite, which is 1. Next thing is about the qx. So if we take x minus 1 whole square, then it will become x minus 1 whole square, then 1 minus x square. If we divide this, and we will get the function like this. And if we put x is equal to 1, separate this both of this term, then the limit will be 0. So x minus 1 is a regular singularity. X minus 1 is also a regular singularity. We can check this. Now, what is a power series method? We are going to discuss next is what is power series method. The basic idea of power series method is for solving ODE is about this ordinary point. So first, assume the solution of this problem as y will be the solution. in terms of x, y is a function of x, which will be in the form of summation 0 to infinity a n x minus x naught whole to the power n. Now if x is equal to 0 is the ordinary point, so we obtain a power series in terms of x only, because x naught will be 0. So yx will be summation and 0 to infinity a n x to the power n. So today we are going to start a new topic, and this topic is will be the extension of the previous video, where we have discussed how to solve a differential equation using power series method. In brief, what was discussed: when a differential equation have a function which have ordinary point and regular singular point, then the solution of that differential equation can be assumed to have uh, uh, to be in the form of infinite series, sum of infinite series, and we can use the power series form to solve that differential equation. Now here is an example. Well, in the previous video we have already discussed what is meant by ordinary point or regular singular point. So ordinary point means at x is equal to x naught if the function which are present in the differential equation does not blow up to infinity, where we need to find the solution of the differential equation. Then it will be called as, and the limit exists, and if that limit is finite, then it will be called as an ordinary point. Now what is regular singular point? Well, if the function does blow to the infinity at x is equal to x naught, but at x minus x naught whole multiplied by the function, or x minus x naught whole squared multiplied by the function does not blow up to infinity, rather it gives a limiting value which is finite, then it will be called, that point will be called as regular singular point. In both of these cases we can assume to have a solution of the form of the infinite series for that differential equation. Now let's see the example. Here we have taken example y double dash plus x square y is equal to 0. We are going to solve this differential equation at about x is equal to 0. If we compare that equation to a general differential equation, which is y double dash plus p of x y dash plus q of x y. So this is not 2, this is y. Let me here, this is q of x, q of x into y. Now here we can clearly see by comparing it with the differential equation that in our given differential equation p of x is 0 and q of x is x square. So we can assume that at x is equal to 0 is a ordinary point. We know that this is x equal to 0 is ordinary point, limit exists, and it does not blow up to infinity. Now we can assume the solution of this differential equation will have the form y is equal to uh, in, y is equal to sum of infinite sum of n is equal to 0 to infinity a n and x to the power n. If we differentiate it with respect to x, then we will get y dash. So y dash will be equal to a1 2a2 plus 3a3 x square. Why? Because you can look at this, a differentiation of a2 will be 0, so d of a naught divided by d of x will be equal to 0 because this is constant. The next thing is uh, what we will get after differentiating. We will get a1 plus 2y a2. Now we're going to write this in terms of summation form. If we put here x is n is equal to 1, then what will get? The first term, let me show you. 1 into a is subscript n, so means 1. Then x to the power n minus 0, so x to the power 1 minus 1, so it will be x to the power 0, so it will be a1 x to the power 0, which is nothing but a1. Like this, we can calculate the other term up to infinity, and then after differentiating the y dash again, we will get the second term. In summation form, we can write it as an n minus 1 x to the power n minus 2. So here also, if we put n is equal to 2, then what we get? Let me show you. N 2, then multiplied by 2, then multiplied by 2 minus 1, then multiplied by x n minus 2, so it will be 2 minus 2. So what we will get? A2 into 2 minus 1 will be 1, then multiplied by 2, so a2 into 2, and x to the power 2 minus 2 will be, this is multiplication, x to the power 0, so it will be answer will be